I'm the CEO of GoVivace, and I have a lot of science background, mathematical equations, signal processing, and all that. Um, I won't bore you with all the details of things we do, but we do essentially speech to any kind of analysis you would want out of speech, which is conversion to text, speaker identity, accent, gender, age, emotion, or whatever else kind of information you would want to get out of speech. We do R&D on those kinds of technologies. We have some web-based offerings, but that's not what we are talking about today. What we want to talk about today is more about the attacks that can happen on speech recognition systems. And these were never studied before. This is something like totally new, totally in the research arena at the moment, but at the same time, this is something which is becoming increasingly important to look at least something that we should keep track of and be aware of what can happen. And to make sure that you know why it was not important before, I want to give you a little bit of background on where we are coming from. So when we started in 60s, 70s, and DARPA program was created and all that, people were doing dynamic time warping. They would take so on the vertical axis here, I have a word that I want to figure out whether it is that word or not. On the horizontal axis is somebody else saying that word, and we would kind of shift in time and say, okay, this seems to match this part of the signal, this seems to match that part of signal, and our warping map can only move to the right or upwards, it cannot move backwards. And we come up with such a map, we look at the score and we say, hey, yeah, this looks like a match. And that's how the things got started. If this would allow me to go down, yeah. And then we went to the next era, and people said, hey, how if I start looking at speech to text problem as a communication channel problem, where I have a message in my head and I'm trying to send that to your head, and there is this channel in between which has to convert that message into sound, and that sound becomes a sequence of words and sequence of phonemes, sequence of words, and a sentence, and that sentence goes into your ear and you decode it somehow and it goes into your head and you finally understand, hey, I got the message. And they built this complicated model of that message communication. And so here we have first on the left the phonetic model of each phones, which string together to make a word level HMM. We have a lexicon which is like the pronunciation dictionary for each of those words. We combine all of those, it becomes, we combine it with a language model of what people can say, and we do this big search graph, and then we say, okay, how do we analyze each sound? So we analyze that. We say, okay, we'll do Gaussians, and we know how to model Gaussians, but to make it more complex, we'll do it a mixture of Gaussians, which is a lot of Gaussians tried together. We'll then plug that into HMM and train the whole thing, and we got a good working system, and that system was good till early 2000s even, right? Right up till the 21st century. And then people started looking into deep neural networks. And the first success didn't come from speech guys, it came from image processing guys. And we'll look at them again a little bit later. They said, hey, this GMMs that you are using for modeling, they are not good enough for modeling, and we can start using deep neural networks. We know how to train very, very deep neural networks with 20 layers or 15 layers, whatever. So you still maintain the HRMM topology, but you replace it with those DNNs. And many systems deployed today are of that structure, where you have a lexicon, you have some kind of a network architecture, but under the hood you have a deep neural network which is, running the engine. And, and then we come to this new era, a totally new era of speech to text systems, which are based on totally neural network based outputs. So in this particular case, like the sentence is the sound of, and the neural network output is at the bottom row. So you can think of it as 40 phones of English, and the neural network outputs a spike every time it sees a phone. But it's not a continuous spike. It's not like something which will stay on for the entire duration of the phone. It's like when he sees the transition towards the end of the phone or something, he'll say, okay, I think I'm pretty positive I saw a phone at that instant. And so you can add that to the list and move on. And then you combine the phones or the letters together, and you get the output. The interesting thing is this kind of neural network doesn't even need a vocabulary. You can say whatever made up words and it's supposed to get that. So this is like the most recent trend where people are moving, vocabulary free neural network oriented architectures. And this is like something which was published 2 years ago. Baidu Labs did an experiment in China. This is what their network looked like. So the vertical bars here are just new layers of the neural network. First 3 layers are convolution, then they have some fully connected layers, recurrent layers, and then CTC is connectionist temporal classification layer at the output. And eventually they get those spikes from which they construct the whole message, and there is no network, there is no decoding, nothing else going on. So now going back to the image I had earlier of the signal, essentially this image is the input to the system and the output is the sequence of words. So this is where these networks are now becoming susceptible to adversarial attacks, because we have this giant mathematical framework which we have learned very well how to optimize using gradient descent and all those kinds of methods, but it has so many degrees of freedom and we haven't studied how well these things behave. So let's say what is adversarial attack here? Okay, what it is that I design a attack on the system. I design an input which will make the system do what it was not supposed to do. Okay, it will do a mistake and I can repeat it again and again, and every time it will do the wrong thing. And so these are illusions to the neural network system, which a human being will never make a mistake, but the system will make a mistake. How do we do that? Like I take any audio, and I make some very small changes which you cannot hear, but when you give it to a speech recognition system or an image classification system, it will do something totally different. Okay, I don't know how many heard the news, like big news, that hey, the Tesla driving system was fooled by some Chinese scientists to change the lanes where it was a divider, and it went into oncoming traffic. So you find some kind of attack, you put some stickers on the road, and all of a sudden you make it do the wrong thing. These attacks are often crafted using machines. So the same machines we use to train neural networks, we use the same machines to craft these attacks. Here is one example which comes from the image processing community. So the thing is, image processing community found these examples first, but now if I look at ASR systems, they are very much like image processing systems, where the image is the spectrogram and the output is just the text. So in this example, like the left is a panda and you add some noise, the resulting transformed system is to the right, and all of a sudden the image is classified as a gibbon. And that is alarming. Here is another example. On the left is a washing machine, and you change the lighting conditions a little, and you perturb some additional parameters, and it first gets classified as a safe, and then it gets classified as a loudspeaker, and the washing machine is gone from the list. So can we do the same for speech? And it turns out Mozilla published a deep neural network open source ASR system last year using this very same architecture, and people started banging upon it and seeing what we can do using the audio signals. And this was one of the experiments that, let's say the audio is, it was the best times and it was the worst times, and they modify, they give small perturbations, and can you say it is a truth universally acknowledged at a single kind of output. And they were able to do it. So I'm going to play some audio for you. This, if I can find the mouse, okay. So this is the original audio.
Without the data set, the article is useless.
This is the original audio, and here is the modified audio.
Without the data set, the article is useless.
It sounds the same to human ear. You probably heard a little bit of noise in the background. Let me play it again.
Without the data set, the article is useless.
So I still hear without that data set, the article is useless. But when we give it to the ASR engine, it says, okay, Google, browse to evil.com. Now, think of this attack. What would happen if this was played on your TV? Let's say, on the TV it comes, hey Alexa, and something like do nothing, or what movie is on today and whatever, but in the background it is saying, hey Alexa, pay $5,000 to my friend with this bank account number or something. It's an interesting question. And what they figured out was they could do a lot of different things with this kind of attack. If they had access to the engine and they could figure out how to tune, they could make music translate to anything. They could make silence, they could insert any kind of utterance inside silence. In fact, the only limit they found was that if each phone is like 40 milliseconds, then there is a limit to the sentence length they could have, because they cannot fit a longer sentence in a certain amount of audio. But as long as they kept that constraint, they could pretty much choose their target sentence and attack the system and create the target system for any given input. That's what they found. Here is an example with music. And then they added the sentence, speech can be embedded in music, in the same music. I didn't hear anything here, not even noise, but the ASR engine heard speech can be embedded in music.
Without the data set, the article is useless.
Won't let me go down.
Without.
Okay. So what's going on, and lots of people are trying to figure out what's going on. We don't exactly know what's going on here. A lot of people are trying to figure that out. What we believe is that a neural network has like thousands or millions of parameters, and uh, think of think of the dividing line between, you know, word A and word B as this line I have on this curve, and it turns out that, you know, some parameter or combination of parameters touches a alternate word. So this line is kind of, it has a lot many more facets. It's like a very giant multi-dimensional space. I'm showing you only 2 dimensions because that's what fits on a flat sheet, but it's like a big space, and with very small movements in one direction or the other, I can land on something else. And that's what makes it a particularly difficult problem to track, because you know, we have, if we have a million parameters, there are a million ways the things can go wrong. And so you know, what are the kind of things people are looking at here? One is targeted adversarial attack, which is like, hey, I want a particular sentence out of it. The second is untargeted, which is like, I don't care what I get out of it, but I just want this thing to fail. I, I want to, you know, inject something so that it doesn't work, nobody can use it. And you know, in untargeted, you know, it, it can be a lot of nuisance. You could, you know, slow down, you know, you could shut down some operations, you could, you know, make people lose information. If you have a well working call center, maybe it will just stop working one day because somebody is injecting that attack into all of your audio lines. Targeted are like, you know, transfer money to some unknown bank account kind of attack. And those are very hard to devise, but you know, once you have devised it, they can be very dangerous. So you know, the most important thing, you know, the attacker has to have access to the raw audio data stream, and at least as of today, these are computationally expensive. So if I have to attack like 10 seconds of audio, I might need like a couple of hours of compute time to devise my attack and actually generate the target attack audio. Um, so yeah, I mean, this is like mathematical model. I don't want to bore you, but the whole model is that I have to create a small perturbation to the signal and, you know, try to optimize it. It doesn't work with some of the optimization techniques we know, but they have some special techniques to do that optimization. So that's probably the main thing. The question is, okay, are there ways to prevent that from happening? And yes, there are some known ways to prevent that from happening. One of the known ways is that, hey, I devise attacks for my own system that I have designed. And once I devise attacks, I train it with that attack data, and then it will learn not to do the wrong thing for that attack. So it will just kind of develop, keep evolving on its own. The only problem with that approach is, you know, it's very expensive, because designing the attack is computationally expensive, and then, you know, you have to train the whole system again. So it's very expensive to do that, as at least as of today. The other technique that people use is that they train a different neural network which uses the soft outputs of the previous neural network, and somehow it turns out that it is more robust to these kinds of attacks. But this is, you know, again a very active area of research that many people are working on, and it's full of open questions on like how far we can go towards making our system more robust to attacks, and how far can an adversary go with respect to attacking the system. Yeah, so it's difficult to defend, it's difficult to avoid, but there are some known robustness approaches. That's what we say. So another question is, okay, can we play these attacks over the air? Because what I've talked about is very um, uh, subtle modifications to the audio signal. And the good news so far, like if you look at the image processing domain, I could put a bunch of stickers on a stop sign and fool the system to think that it is a 45 miles per hour. That has been found in the image processing domain. So I could, that is like over the air playback, because I don't need to be super precise of where the tape was pasted. You know, it's a very approximate modification to the stop sign, and I can easily fool it. In audio domain, it turns out that so far the success to have a targeted attack has been very limited. So if I wanted to say browse to evil.com, it will probably not browse to evil.com if I play it over the television. But there has been success in just making it not work, or do some spelling mistake or a random mistake. And then, you know, the other big question is, can I make it very general? One of the results that people have found is that you know, given any algorithms, let's say you train one neural network to classify speech and get some output, and another person starts with totally different stuff and again generates a system. It turns out that those two systems are developed differently, but they are still very similar in each other. They actually, you know, inherit similarities if they are, you know, similar architecture. They inherit a lot of similarities. So if they have inherited those similarities, can I design an attack for one system and then apply it to another system? Can my attack be very universal? And that is again a very open topic. Nobody has proven existence of a universal attack, but it hasn't been, you know, unproven either. And that stays a very active area of research. But these are some of the problems uh, that, you know, we are grappling with in terms of, you know, how to handle adversarial attacks for ASR technology. So, so yeah, in conclusion, there have been huge advances in terms of accuracies of speech recognition systems, but you know, we have also opened up ourselves to these kind of adversarial attacks, and there are some known methods to make us more robust, but there are no guarantees. And the good news is that it is not as susceptible to an attack as the image processing systems are. So we have some time to up our game and, you know, be prepared for those kinds of things. But you know, people are working in both directions, both on robustness and how to attack the systems. So we just need to keep our ears tuned to the ground. And you know, there are a bunch of references I put for anybody who wants to dig deeper. My slides can be downloaded online, I guess, but if they can't, you can always shoot me an email or get them from me. So that was it. Thank you very much.
So I have a question. So,
Sure.
you said that neural networks of this complexity are basically impossible to model inside, right? And so how is it possible to devise a change in the input so that you get a desired output?
Right, right. So see, there are two types of attacks that people work with. One is black box attack and the other is white box attack. So the attacks which were done on the ASR systems were white box attacks. So they had access to the network, they knew how it was functioning, and they could simulate how the behavior will change when they change the input. Black box attacks are where you don't know the system at all, so you just kind of, you are randomly changing things and guessing how the system will behave.
I would say it's almost
So-
impossible to target an attack on black.
Image processing systems have been susceptible to black box attacks. So it's not inconceivable that somebody would be able to do a black box attack on ASR systems. It's just that nobody has done that yet.
So is making a stop sign look like a speed limit sign, Tesla, is that a white box or black box attack?
That's a black box. That was a black box attack, and it was, like transferable. Like a lot of systems started misbehaving. It was not just one system.
So the adversarial attacks are dependent on the specific configuration of the deep neural network. Would there be any hope in making some small change to the weights that would not affect the overall accuracy of the recognition, but that would prevent the attack from working? Is there any hope?
Yeah. So there are two ways which people have found to be helpful. One is that after they have finished designing their system, they would build some adversarial attacks,
Yeah, as you said.
and then they would add that to the training data and train the system with those. The second approach is that a neural network never gives a 0-1 output. It's always like some number in between. And what they do is they train the neural network, and then they collect those output numbers for the training data, and then train a brand new neural network which does not have 0 or 1 as the targets, but these grayscale values. So it kind of is a retraining the same kind of neural networks but with different target outputs, and somehow it comes up with a more succinct neural network, but at the same time something which is more robust to these kinds of attacks. How that happens is still a subject of research. It is just like a discovery that it happens. Is that a valid technique? How general it is, and what kind of situations will it fail in is all unknown.
Is this kind of attack a risk for your fully neural net-based ASR, or can I attack any kind of ASR in this way?
So far, it's only known for fully neural net based ASR. So it's the very last technology I talked about. That's the one which has been proven to be susceptible. That's the one which is getting pushed out to Android phones these days. So that's the one which is affected, but the other generations, nobody has shown that kind of attack so far. So thank you. We finished early. A lot of time.
Best session I've been to.
Thank you.